So we're going to start looking at statistical inference. And I really today just want to scratch the surface, just sort of introduce some ideas. But this becomes very important. This is typically spoken about as the most important idea in research methods or statistics. And it's a deceptively simple thing at first, but it's a bit like measurement, and it's closely related to measurement. When you get down to the details, it can get rather tricky. So we'll take our time with it a bit. So normally what I would do if we were doing this in a classroom, I'd probably turn up with a big bucket of candy or something and get you to physically measure it in some way, and we'd do some calculations and whatever, but can't do that. So I've had to do the work myself. So what I'm using here is a kind of candy. This is, for those of you, many of you from other countries may not have ever heard of these. These are called Smarties, and these are the things that were copied to become M&Ms. And they're still very popular in Australia. They were invented in the UK. So I started with a bag of what was labelled 120-gram bag of Smarties. And the question here is, how much does a Smartie weigh? So one way to do this is open the bag, just put all of the Smarties onto a set of scales, weigh them, and then count them, and divide the number of Smarties into the weight, and that would give me the mean weight of the Smarties. And indeed I did that, and I'll tell you the answer later. So that's one way of doing it. That's not so easy to do if you've got a shipping container of Smarties and you want to work out the average weight of the Smarties for some reason. You're not going to, open all the packets and weigh all the Smarties and then put them back in the packets and put sticky tape on them or something. You're not going to do that. So what we do in the real world when we are faced with these questions, and we are quite a lot, is we take a sample. So in the Smarties factory, I can guarantee you they take regular, probably daily, maybe hourly samples, and they will measure things like the weight and the dimensions of the sample, just to make sure that the factory is doing what it's supposed to do. So let's talk about a little bit of the language here. So when we say a representative sample, what we mean is the characteristics of the sample, the ones that we are interested in or that are going to influence what we're trying to examine, are likely to be present in the same proportions, if you like, in the sample as they are in the population. And when we do this, whenever you want to get a representative sample, you've got to think carefully about what is the population that you're interested in. In this case, we'll just say the population I'm interested in is my bag of 120 grams of Smarties. Okay, I'm not interested in the daily production from the factory or the annual production from the factory. I've just got a bag here, and I'm just curious about what a Smartie weighs. And I don't particularly want to weigh every one of them. And perhaps I have a tiny set of scales which only weighs up to 5 grams, and I don't want to sit there and weigh the bag of Smarties 5 grams at a time. So what I have to do is get a representative sample. Now, there are different ways of doing this in different situations. What is often described as the gold standard, the best way, is to take a random sample. And what we mean by a random sample in this case is a population is the Smarties in the bag, and the random sample would mean that every Smartie in the bag has an equal chance of being selected for my sample. Okay, that's the definition of what random sampling means. So how do I achieve that? Well, what I actually did was I tipped the Smarties into a bowl, and I got a spoon, and I stirred them around, and then I took a bunch of them out of the spoon. Well, I picked a bunch up with the spoon without looking at the bowl, closed my eyes, and I chose 11. Now, so that's my sample. So there's my sample. There's 11 Smarties, and I weighed them with a little pair of scales that claim to be accurate to I think it's 100th of a gram, and I have checked them against calibrated weights, and they're pretty good. Okay, so I'm fairly comfortable using 2 decimal places there with the weights. So that's my sample, and there is a box plot of the weights, which you all know how to read now, and there is a density plot. And when you look at the density plot, you look at that and you say, okay, it's not, there's a little bit of a bump there. Wonder why. Don't know. It's not, when I look at that, I'd say it's not outrageously weird, but it's not it's certainly not a perfect, normal distribution bell curve. And you can tell looking at the box plot that it's skewed to the right a little bit. So we've talked about the population. Now, because in this case, I can do a pretty good job of getting a sample of what's in the bag. What I can't do just by looking at a bag is get a sample of what's, what that day's production was from the factory. If I worked in the factory, I could. There would be ways of doing it, but I can't do it. I've just got a bag that I bought from a grocery store on campus, and I've taken a sample. So all I'm going to make claims about is my bag. So it turns out when you do this, if you get a sample, if you get a representative sample from something, you can do a calculation to work out something that's called the standard error. Okay. And the standard, I'm just going to introduce some of these ideas today. We're going to talk a lot about these things, but the standard error is, it's a number which represents, it represents the error that is due to the fact that you are measuring a sample and not the population. So what I'm going to do is calculate here the standard error for the median. Now, I'm aware that there are quite a few students in the course that have already done a statistics course, and you will have learned about the t-test. And when you do the t-test, what you do first is you calculate the standard error of the mean. And I won't do that here, but I will probably show it to you at some point. All right, I'm going to do this from scratch. Show you how it's done. So that's our data. Now, I could do this the canonical way. Okay, I'm sure now you all know what the canonical way of working out Q1 and Q3 is, but we'll actually do it the Excel way, which is usually near enough. Okay, for most purposes it doesn't matter. So what we need here for to work out the standard error is we need to know the interquartile range. We need to know the number of Smarties we have in our sample. So we know already that n equals n is 11. Okay. And then, sorry, can everyone see? I'll just get this in line here properly. Okay, that's good. Okay, so n is 11. We know that. Now, it will be useful for us to know the median. So let's work out the median. So we just use the median function in Excel, and we just run that down there. And that tells us that the median is 0.98. I don't know why I've got the right one, but we'll just yep. Okay, so do it there. Okay, so that's straightforward. Now, to get the interquartile range, we need Q1 and Q3. So let's start with Q3. So the function you use in Excel is called quartile.inc. So that's inclusive quartile. So we highlight the data, and then we tell it which quartile we want. So we want number 3, quartile 3. So we have the first thing, the F4 to F14 there, which I hope you can see. That is our data range, and the 3 is the quartile that we want. Okay, so it gives us 1.06. And then for Q1, same idea, quartile.inc, and then we highlight it. And this time we're going to put 1 for quartile 1. And then the IQR is just the difference between those, so Q3 minus Q1. Okay, 0.04.
You got the median instead of the Q3.
Sorry?
The IQR, you got the median, you highlighted the median instead of the Q3.
Did I? Oops. This is in Q3.
No, when you did the IQR, you highlighted the median instead of the Q3 minus Q1.
Oh, did I? Oh, okay. Sorry. Yeah. Confused there. Okay. That's better. 0.13. Thank you. Okay. So now what we can do, so there's a little formula we use to get the standard error of the median. So I'll write it around here for you, and you can make a note of it. Okay, it's very simple. So we'll call it so computer's not helping. Standard error equals IQR divided by 1.08 times the square root of n. Okay, so that gives you a reasonable approximation to the standard error for the median. So IQR divided by 1.8 times the square root of n. So let's do that calculation. .03. So what this is telling me is that, So what I'm trying to estimate here, what I'm doing here is I'm trying to estimate the median weight of the Smarties in my bag. And what I've done is I've taken a sample of 11 and I've done this little calculation that's given me this thing called the standard error. And what the standard error tells me is this is how much error, if I use the median of my sample as my estimate of the median for the whole bag, then there will be a certain amount of error in that estimate due to the fact that I'm using a sample and not the whole bag. And that estimate is expressed as the standard error, and it's 0.03 grams. Now, the way we use this typically is we use this to estimate what's called a confidence interval. So a confidence interval is a range about which we have a degree of confidence that in this case the median falls. And we nearly always use 95% confidence interval. So I'll just show you quickly how we calculate that. So we'll have a CI upper, that's the upper range of the confidence interval, and a CI lower. So the CI upper is going to be the median plus, we will say for the moment, 2 times the standard error, okay? So it's the median, that's 0.98 plus 2 times the standard error. And the lower, whoops, the lower is going to be the median minus 2 times the standard error. Okay. Okay. So we can say we are 95% confident the median weight of the Smarties in the bag is in the range from 0.91 to 1.05. Okay. So that's the conclusion. Now, there's a whole lot of things we've got to learn about this. So first thing I'll just say, because somebody is almost certain to point it out to me, is when we do this normally, it's not the median plus 2 times the standard error, it's the median plus 1.96 times the standard error. I'll come to that later in the course, but for practical purposes, 2 is fine. So that's one thing. The bigger issue and the trickier issue is, what do we actually mean by 95% confident? And what we mean is something like this. The strict interpretation of it is, if I repeated this procedure 100 times, so 100 times I took a random sample of 11 Smarties from the bag, so then I would expect that 95 out of those 100 times, at least 95 out of those 100 times, the median weight of my sample would be between 0.91 and 1.05 grams. That's the strict interpretation. Now, just so you know, there were actually 119 Smarties in the bag, and the median weight was, the population median was 1.01 grams. Okay. So that, in a nutshell, it's just a little toy example, but that illustrates the basic principle. Now, the interesting thing about this is, so I did this with a bag of 119 Smarties in it. if I went to the Smarties factory and there was a big container with 1 million Smarties in it, and I was able to take a random sample of 11, the estimate for the 1 million Smarties would be exactly as good. It will be no different. You'll see in the formula that we used there is nothing in that about the size of the population. It's only the size of the sample. So this is why, you know, when we have elections and we have political pollsters, and they typically will take a representative sample of 1,000 voters, they can draw conclusions about a population of, I guess in Australia, I don't know, 10 or 20 million voters. As long as the sample is representative, you can use a calculation like this. But there are many types of calculations like this, but you can use a calculation like this to get an estimate. And what you get is an estimate with a confidence interval. So those of you that are familiar with political polling will know that the political pollsters talk about margin of error. And the margin of error is 1.96 times the standard error. It's usually about 3%. And that's how it works. So I've just done it with a bag of Smarties, but you can do it with many, many things. So this is actually, when we talk about, when people talk about statistical inference and statistics more generally, a lot of what they're thinking about going on actually involves this principle of getting a sample from a population and doing some kind of statistical test on it or a statistical model, like a linear model, and you come up with a conclusion which can be expressed in the form of a confidence interval. So you can do this with linear regression, for example. With the linear regression examples I showed you, I can produce confidence intervals for the adjusted R squared and for the beta coefficients and the intercept, assuming I'm working with a sample from a population. So I think that's about time, but I can stay around for questions and discussion if anyone would like to. Tomorrow's tutorial, we're basically going to be talking a bit about critically appraised topics, and if I have enough time, we'll have a look at a meta-analysis, which is a particularly important kind of academic research paper that you should be interested in. So thank you for coming today.